Global financial markets and logistics networks rely on timestamps accurate to the billionth of a second to prevent the system from falling into data collisions. Keeping that rhythm steady depends entirely on a network of machines hovering thousands of miles above the planet. These orbital instruments are painstakingly assembled in sterile rooms, engineered to measure time with atomic precision before they launch into the vacuum of space. Without this constant alignment, errors in satellite calculations would grow by several kilometers every single day, rendering modern navigation and logistics useless within a week. Soon after deploying the first global positioning systems, engineers monitoring the telemetry noticed a persistent drift in the orbital clocks. Every single day, the satellites were gaining exactly 38 microseconds compared to the synchronized atomic clocks sitting back on Earth. Post-launch diagnostics confirmed the hardware was performing exactly as designed, with no detectable software bugs or mechanical flaws in the schematics. The instruments were measuring time flawlessly. The discrepancy emerged because the physical space they were traveling through operates under a different set of rules. We usually picture space as an empty container where things happen, and time as an independent clock ticking steadily in the background. Physics models them instead as a single interwoven entity, a four-dimensional fabric blending length, width, height, and time into one continuous structure known as spacetime. When a massive object is placed onto this fabric, it creates a physical dent, stretching the dimensions around it. We feel the effect of that physical depression as the downward pull of gravity. Because space and time are fused, a planet's mass bends physical space while simultaneously slowing down the passage of time. To observe the severe end of this effect, we must look far beyond our solar system to regions where mass reaches extreme densities. Black holes create the deepest gravitational wells in the cosmos. As depicted in the film Interstellar, the space-time compression near these regions is so severe that a few hours spent near the event horizon equates to years passing back on Earth. Our planet is a relatively small, isolated body, drifting in a quiet stretch of the galaxy. Yet Earth possesses enough mass to warp the geometry of its immediate surroundings, subtly altering the clock for any machine we put into orbit. Gravity, however, is only one half of the physics equation acting on the satellite network. They also have to contend with velocity. The principle of time dilation dictates that the faster an object moves through space, the slower it moves through time. Hurtling around the planet at thousands of miles per hour forces the onboard clocks to tick slower, resulting in a loss of exactly 7 microseconds a day. But these satellites also operate 12,000 miles above the surface, far removed from the deepest part of Earth's gravitational dent. Operating in that weaker gravity forces their clocks to tick faster than those on the ground, directly fighting the effect of their orbital speed. To find out exactly how much time the satellites experience, engineers have to balance the gain from altitude against the loss from speed. This diagram illustrates the mathematical balance. The weaker gravitational field high in orbit causes the clocks to add exactly 45 microseconds to their day. At the same time, their massive orbital velocity subtracts 7 microseconds. When combined, the net difference is 38 microseconds. This 38 microsecond drift represents the exact mathematical intersection of general and special relativity. To account for this, engineers intentionally calibrate the satellite clocks to run slightly slow while they are on the ground. Once they launch, the altered physics of orbit corrects the math. Without these daily mathematical corrections, our entire global grid falls completely out of sync. Every map on your phone, every digital transaction, and every flight path relies on this constant adjustment. Spacetime is an invisible, active mechanism shaping the structure of our daily lives. Subscribe to keep exploring the physical forces that govern our universe.